So good afternoon, everybody. My name is Giorgio Marfella, and I'm the chairperson of the Architects Registration Board of Victoria. Today we have a webinar which is on roof drainage for low-pitch metal roofs. And before starting the proceedings, I will begin, as always, by acknowledging the traditional owners of the lands in which we are all situated. In particular, I wish to pay my respects to the Wurundjeri people of the Kulin Nation, and I pay my respects to the elders past and present. So today's presentation is part of a series of webinars of the ARBV that are valid for more continuing professional development. And I remind all of you present here today or watching this presentation also possibly in the future that CPD is a mandatory legal requirement here in Victoria for architects, and that also CPD compliance is monitored and audited by the ARBV. Now, the ARBV is committed to proactive education to support architects in refreshing and uplifting their competencies. And part of this interest is also to promote good documentation practices. Now, as you know, the Victorian Code of Architects, Code of Conduct for Architects in Victoria expects a reasonable level of knowledge, skill, and care. And part of that requirement extends also to technical competencies, for which, of course, the design of building envelopes and roofs is a critical part of the work that architects provide to their clients and to the public at large. And so today's presentation will focus on one particular technical aspect, which is the design of flat pitched roofs. And this is because architects often hold a very important role in the design of these roofing systems. And they act very often as lead designers in projects where they become also responsible for the detailed design of these systems. Now, needless to say, architects have to work in collaboration with consultants, specifically, in this case, structural engineer or hydraulic engineers. Certainly, larger projects, the role of hydraulic engineers should always be contemplated. But also, there's an element of smaller project in which architects may have to do a bit of legwork themselves. So their role, in any case, whether with consultants or with less consultants on the board, they still have an important role to play. So at this point, I think I'm ready to introduce today's speaker, and we have the pleasure of having Rowan and Gregory. Rowan has an extensive experience in the design and construction of roof drainage system. His background is structural engineering, but he has also significant experience as a forensic engineer. So as you will see, there will be quite a lot of very useful information today from this presentation. So we're very much pleased to have Rowan here to speak for and present for the ARBV. But I will return after Rowan's presentation, which will run around 45 to 50 minutes. If time allows, then we can have some questions and answers. So at this point, Rowan, I can hand over to you. Thank you.
Oh, thanks very much, Giorgio, for the introduction. And I just want to take this opportunity to thank particularly Isabel Legg and Carly Hunter of the ARBV for making this presentation possible. There's a fair bit to get through, so I'll go reasonably quickly. So the first thing is to say it's surprising the extent of this problem in Australia, and it applies to all building sizes and building types. Roof drainage for low pitched metal roofs, and in particular for box gutters, is really done very poorly. I think it's probably the worst part of the construction industry. It causes a lot of a large amount of costs to insurers and building owners, but this really needn't be the case. And I think from the architect's point of view, the one point I really want to get through today is that correct detailed design and documentation of roof drainage at building permit stage is essential, and it will de-risk your building. I'll just start by a small example. This is an expensive house in Kew. This was investigated by a forensic plumber about 5 years ago. And just to give you an example of what the owner had been putting up with reasonably regularly for a period of time. Now, I'm told that she, after locating those buckets, not long after, she walked out of the room and the ceiling collapsed. And really, this sort of thing shouldn't be happening in Australia. We should be able to do better. Now, this was actually rectified with some dam buster products, which I'll talk about later, and there have been no problems in the last 5 years. So I'll just go through now the topics that I want to run through briefly. Number one, why are box gutter systems currently so problematic? The good news, there is a simple solution. The regulatory framework in Victoria in particular. Just some general comments on compliance with the NCC. I'll just present design flow rate. I'll go through the main underlying principles of NZS 3500.3 Stormwater Drainage Code. I'll talk about whether box gutters can change directions. I'll have a look at deemed to satisfy solutions as per the code. I'll have a look at performance solutions. I've got a small, interesting little segment on valley gutters where they can be problematic. I'll talk about access to box gutters for maintenance and cleaning. I'll run through a couple of design examples. I'll show some examples of non-compliant roof drainage, and then I'll just finish up with giving you my thoughts on how the industry could be fixed. So, number one, why are box gutter systems currently so problematic? Well, I think it's a combination of reasons. Firstly, and probably most importantly, roof drainage is either not documented at building permit stage or not documented well enough. Even when hydraulic engineers are engaged to specify roof drainage, they often don't do it very well. They rarely, if ever, specify both the upstream and downstream box gutter depths. However, this information is fundamental to determining whether the box gutter system will fit within the architecture and the structure. Very commonly, particularly in domestic construction, the design of the box gutter system is left up to the roof plumbers, and this really should never happen. The two main points are, firstly, plumbers typically simply don't have the skills to carry out the hydraulic design. And secondly, at the time they get involved, which is typically framing staged, it is often difficult, if not impossible, to find a compliant solution that fits within the architecture and structure without having to make significant changes. And as they must complete their work, they very often install a non-compliant installation, which has serious consequences. Now, I don't think roof plumbers should get the blame for this at all, really. I think the problem is at the design end. I mean, the roof plumber, they've got a very difficult job practically, and they shouldn't have to worry about design as well. And there is another issue, is that the Stormwater Drainage Code is quite limited. It only has 3 types of box gutter overflow devices. And it's very hard to find solutions with only those devices. Now, there was a lot of research done in roof drainage in the late 1990s, but for some reason there's been no development of that code in the last 25 years with regards to box gutters. They've really just tinkered at the edges. Whereas at the same time, there's increasing use of box gutter systems on buildings, and really the money should have been spent on continuing work on that code. So the good news is that I believe the current problems in the industry, which are extensive, are eminently fixable. The first point to make is that dambuster products, which have been on the market now for over 5 years, provide a lot of additional solutions, but importantly, change of direction, and which means that in combination with the code devices, there really should always be a solution. You should always be able to find a solution at the design stage. And it's very often ends up being a combination of those, the different devices. As I mentioned before, it's crucial that this is done well at building permit stage, and you really need to know, everything needs to fit. You need to ensure that your roof drainage system fits within the architecture and the structure, and that you know that you're not going to end up with bulkheads where you don't want them. And also this information needs to be provided to the roof truss fabricators for coordination purposes. And particularly now that there are also more and more metal roofs, it's extremely difficult to change a metal roof once it's been erected. So next point is that I think architects have got to stop half specifying roof drainage. It really just leads to problems. It needs to be done properly. And building surveyors are critical in this role, in their role of they're really the gatekeepers to documentation, and they've got to stop accepting building permit documentation without a detailed roof drainage design. So I think you know, up until now, building surveyors have, particularly in Victoria, have sort of thought, well, you know, roof drainage is within the PCA. It's okay just to leave it up to the roof plumber, but it's not okay, and it's to my way of thinking, it's passing the buck, and roof drainage falls within all 3 volumes of the NCC, not just the PCA. Now I just wanted to show you on the left-hand side of the 3 code devices. Then there are various dambuster products on the market. I'll go through those a bit more later. There are also the AHSCA Research Foundation have developed, did a lot of testing up on the Sunshine Coast. They've developed quite a lot of individual solutions, and in particular, they go a long way above the code limit of 16 litres a second. So I suppose again, my main point is that that you really should be able to find a solution at building permit stage, but it requires coordination with the architecture and the structure. Now, before I start on slide 3, I've just been asked to read a short paragraph, and that is, architects should be aware of their obligations under the Architects Act 1991, the Architects Regulations 2015, which includes the Victorian Architects Code of Professional Conduct, and the Building Regulatory Framework. Architects must have detailed understanding of construction and work closely with builders and other practitioners in the building industry. So just on this slide, on the left-hand side is the Building Regulatory Framework. So the Building Act calls up the building regulations and the plumbing regulations, both of which call up the National Construction Code. So the now we have obviously BCA volumes 1 and 2, and the acceptable construction practice has been removed from volume 2 and put into the housing provisions. But all 3 volumes really end up back at 3500.3, and you can either have a deemed to satisfy solution in accordance with 3500.3, or a performance solution, or a combination of both. Now, in Victoria, the plumbing regulations call up 2 additional documents. There's HB 114/1998, which is that's quite a good document. It goes through worked examples from 3500.3, and then HB 39 it is the code for metal roof and walling, and there was some sizing information on that, which wasn't actually terribly correct, but it's been corrected now. In the PCA says that 3500.3 takes precedence over HB 39. So just recapping on a few notes from the previous slide. So roof drainage falls within all versions of BCA volumes 1 and 2 and the PCA. 3500.3 takes precedence over HB 39 in terms of sizing. Now, the next one's an interesting one. In Victoria, my understanding is that you need to comply with both the building regulations and the plumbing regulations with respect to roof drainage. And so to me, that says it is a building surveyor's responsibility and that they shouldn't palm it off onto the roof plumber. Yeah, okay. I'll go to the next slide. So the first question, can you prepare a performance solution to modify the requirements of HB 39, the Handbook for Metal, Roof and Wall Sheeting? But I'll just give you a minute to think about that and read the questions. And the answer to that is A. No, as HB 39 is called up directly by the plumbing regulations and not by the NCC, you cannot modify HB 39 by, you can only modify HB 39 by applying for a modification with the Building Appeals Board, Victorian Building Appeals Board. Now, I just want to talk a little bit more about HB 39. There was a very significant amendment that came out in mid-2021, which was not very well publicised. Now, on the left, we have figure 5.7.3. That was the amendment was the deletion of this figure. Now, this figure had always been inconsistent with 3500.3. There was actually never any method of designing this in accordance with 3500.3, but it was used as an excuse for what I'll call the Ned Kelly style rainhead. So since mid-2021, these have been unacceptable, yet they're still very prevalent. The only DTS solution is in fact the open-fronted rainhead in accordance with the code. Now the dambuster rainhead is available under a performance solution using standard performance solution templates, and that has two main features. Firstly, it has a box gutter receiver, and that allows you to get a good siliconed and riveted seal between the box gutter and the rainhead. And the second main feature, it's got a very high overflow capacity with a vertical overflow chute. So the water when the downpipe locks, the water overtops the weir and goes straight down. And it may be effective for hail to some extent. We really are not sure. Interestingly, the code says that the box gutter must be sealed to the rainhead, but it doesn't show you how to do that. And forever, it's not being done properly. Typically, people will just cut a hole in the back of the rainhead. They'll poke the box gutter through, and if you're lucky, you get a bit of silicon. But that's exactly where the water gets into the building. So I don't know why that has not been defected. It's just so common. Now, I'll just go through, I'm sure most of you are quite conversant with this, but I'll just go through quickly compliance with the NCC, which is a performance-based code. So essentially, the NCC has performance requirements, and you need to meet them with either a deemed to satisfy solution, a performance solution, or both. You also need to provide with your solution, whether it's deemed to satisfy or a performance solution, you need to provide adequate evidence of suitability. So interestingly, for, if you go on to, if you delve into what's going on in practice, roof plumbers are installing roof drainage, but they rarely, if ever, carry out computations and drawings. It's been a bit of a free for all for some time, and that needs to stop. But I understand the on the checklist for the VBA checklist, it says that the first item is a question that says, has the installation been sized correctly in accordance with 3500.3? It really should say, have the computations been carried out, and where are they? The evidence should be provided of them. But moreover, look, plumbers shouldn't be designing roof drainage anyway. So yeah, just I'll just flick through these. As I said, a combination of solutions is you have a combination of deemed to satisfy and performance solutions. Excuse me. The next, I'll just run through quickly the design flow rate. That's simply the catchment area multiplied by the 1% annual exceedance probability in millimeters per hour. That was formerly called the 100-year event. So 1 millimeter over a meter squared essentially equates to 1 litre. So if you just multiply the catchment area by the 1% AEP, you'll end up with litres per hour, but we want it in litres per second, so we just divide by 3600. The other thing to note is that the catchment area is defined as the plan area plus half the net vertical area, which allows for driving rain. And in this example, the internal bay, the catchment area is simply the plan area because the net area is 0, whereas in the end bay, it's the plan area plus half the vertical area. Now, there are two methods to determine the design flow rate. The first one is you can find the nearest town in the tables in 3500.3. And the second one is, which is the one that I prefer, is you can go to the Bureau of Meteorology's intensity, frequency, duration website and just insert the latitude and longitude, and then it will bring up a table of the various annual exceedance probabilities. So we work on a 5-minute period concentration period, and the 1% is for the design of box gutters and the overflow condition in eaves gutters, whereas the 5%, which was previously the 1 in 20 year return period, is for the design of eaves gutters in the normal flow condition. But importantly, you need to use in all applications, you need to use the 1% AEP in the overflow condition, because fundamentally you don't want your building to flood in a 1 in 100 year event. So just a question number 2, what's the design flow rate for Melbourne City at the 1% AEP? And the answer to that is 187 millimeters per hour. And just to note that it's quite not so variable within metropolitan Melbourne, but around country Victoria, it's quite variable. And the smallest value I found is 127 in Colac and 237 millimetres per hour in Mallacoota. The next topic is the main principles of 3500.3. Now, it might appear to be quite a complicated code, but it really boils down to three very simple governing principles. The first one is that freeboard must be maintained in all locations throughout the box cutter system. Now, in the design flow condition, that's actually 60 millimetres for all three code overflow devices, which is 50 millimetres plus 10 millimetres allowance for turbulence. And in the overflow condition, it actually varies. It's 60 millimetres for the rain head, where free flow is still maintained. It's 30 millimetres for the sump and side outlet, and it's 45 millimetres for the sump and high capacity overflow device. So both those second two devices are hydraulically very complicated because the water level needs to rise up to either get out the overflow duct or over the overflow weir. So the box gutter and the overflow device are integrally related and designed together. The second important aspect of fundamental aspect of the code is that there's a minimum design flow rate of 3 litres a second. Now that's not terribly clear in the code, but all the tables start at 3 litres per second, but the code just doesn't say that that's the minimum. Now, Associate Professor Terry Lukey, who is the leading expert technically on roof drainage in Australia, has written a paper on this to confirm that that is in fact the case. And the reason for you really need a minimum design flow rate so that it effectively dictates minimum sizing. And if you take that to the extreme, for example, if you had a flow rate of 0.2 litres a second, you might say, well, I can have a 25 millimetre diameter downpipe, and that might work fine hydraulically, but we're not talking about clean water. We're talking about water that's contaminated with debris, and that's why you need minimum sizing. Now, 3500.3 is currently limited to a maximum flow rate of 16 litres a second, and that's really simply due to a lack of research and development. So it just needs more funding to expand that, but the AHSCA Research Foundation has gone well above that 16 litres a second, but you do need to find someone who belongs to that association, has done the required training courses to use their software. And the third important point is that the overflow capacity must be at least equal to the design flow capacity, i.e. the 1% AEP. Now, piped overflows from sumps must discharge visibly to atmosphere and to the surface drainage system. Very often I've seen two pipes in a sump and they both go to the underground drainage system, which is really a bit silly because when the primary downpipe locks, it overflows into the overflow pipe, still goes into the underground drainage system, and you don't know that the primary downpipe is blocked. There's some recommended technical reading in relation to 3500.3. There are three papers by Associate Professor Terry Lukey, which are all very technical and very good. There's also a technical appraisal of the Dambuster roof drainage system by Adjunct Associate Professor Robert Keller. And that, if you read through that, it will give you a much better understanding of 3500.3. Excuse me. Now, can box gutters change directions? Well, as you can see, in practice, they do. really, as I was saying before, the code devices are very limited, and we really do need a way of changing directions. Now, so I'll ask let you read the following question: Can box gutters change directions? Look over to the answer. So the answer is sort of yes and no. Under 3500.3, box gutters must be straight without change of direction. And there's a very good reason for that, is that when you change directions, let's say we have a 90-degree bend, the water builds up in the outer corner and you lose your freeboard. So that's the main reason why you can't change directions, because you increase the risk of failure and you'll lose the minimum freeboard required by the code. But if you introduce a vertical step, which the dam buster devices do, and that step is great enough to, one, overcome the loss of energy in the bend and loss of freeboard, then I really believe there's no reason why you can't change directions. It's just going back to that fundamental requirement that the devices were all designed around the freeboard being maintained at that critical location. So I'll just go quickly through the deemed to satisfy solutions to 3500.3. Now I've redrawn the open-fronted rain head, and I've shown to the dotted line just to show the overlap of metal components, which should be 25 millimeters, to enable that to be siliconed and riveted, with rivets spaced at not more than 40 millimeter centers. Now that is not shown. That diagram the diagram in the code doesn't show that overlap, but I think that it should. So yeah, the open-fronted rain head is well, it works really well, but it's not very attractive, and I'm sure all of you as architects would not want to see this on your buildings. The second one is the sump and side outlet, where when the downpipe becomes blocked, the water level rises and escapes through the overflow duct. And you could have water coming from either both directions or one direction. The code only shows it from two directions, but I think I can't see any problem myself with that being designed in accordance with the code for one direction only. The third type of device is it's quite a complicated device, but it's also quite a clever device. That's the primary downpipe. When that gets blocked, the water rises up and flows over the two weirs and down into the overflow downpipe. Now that's the capacity of the downpipe is dependent on just two factors. That is the head of water over the downpipe and the size of the downpipe. So with this arrangement, both the overflow downpipe and the primary downpipe are located at the base of the sump. They've got the same head of water, so they've got the same overflow capacity. Now you'll rarely see this constructed. Instead, I'll look at this on another slide. Instead, they construct a standing overflow pipe, which is non-compliant. So question 4, for the sump and side outlet and sump high capacity overflow, is the design of the box gutters independent of the design of the sump? And the answer to that, is I've discussed, is C. Well, yes. Oh, sorry, I'll explain that better. In the normal flow condition, the flow in the box gutters is described as free flow. So the water just goes straight into the sump or the rain head, straight down the downpipe, and is not interrupted. In the overflow condition, which is the critical design condition, the box gutter and sump must be designed together, because backwatering must occur for water to flow into the side overflow duct or over the internal weir and into the high capacity device. So this is actually very complicated hydraulically. Now, as I mentioned, you'll often see the high capacity sump incorrectly constructed. In fact, they often use, for the overflow pipe, they'll use an inverted pop, so it only it might only be 40 millimeters above the sole of the box gutter. Now, that is the code does not allow you to design that device. It's a non-compliant device. But I will point out that the AHSCA Research Foundation software can design a standing overflow pipe. So a quick look at the dam buster devices. As I explained before, the box gutter receiver permits a good seal with the box gutter, and it's got with the internal weir, it's got a very high overflow capacity. The next main product is it's a side outlet and rain head combination. So the side outlet, it's not really a sump, it's really a change of direction device. So that we have the vertical step, and then the water goes out through a short, deep box gutter section, and which connects to the back of the rain head. There are different configurations for the side outlet. There's a T shape, an end, a corner, and a cruciform, and they are actually supplied in two sliding pieces which makes them easier to install. But there's plenty of information on the Dam Buster website if you need to know more. The next device is it's the Dam Buster sump. It's almost like an internal rain head. The flow is in one direction only, and so if the primary downpipe blocks, it overflows the internal weir and goes down the overflow downpipe, which must, as I said before, discharge visibly to atmosphere and the surface drainage system. Now, this device has also got an extra safety feature, which is a full blockage overflow indicator, and it's recommended that is used where possible. May not always be possible. In the Dam Buster manual, there's a section that discusses risk management, but without the full blockage overflow indicator, there's not much difference between the Dam Buster sump and the high capacity sump in the code, in terms of the risk of failure. And you can join them up in series, and when you do that, one of the wall between the box gutter and the next series is cut down to allow, just in case for some unusual reason, both the primary and the overflow downpipe blocked, water could then flow into the next series. That's just an example. This was a retrofit situation where we just had to change directions. So there's the box gutter changing directions at a Dam Buster elbow, going into a T-side outlet and then into a rain head. Just one point to note about this installation is that where where you're stuck with existing shallow and non-compliant box gutters on a pitched roof, you can install a transition flashing at a lower slope to give you a bit of extra depth. So you might install that at, say, 4 degrees, and that will allow you to gain extra depth to get a compliant installation. Now, next one is a detail that I see quite commonly is the architect might show a combination of a sump and a rain head. Now, there's two problems with this. Firstly, in this case, it's got the sump can be designed as a sump inside overflow, but the problem is when that overflows, it doesn't discharge visibly to atmosphere. So you could have a blockage in the pipe between the sump and the rain head. It overflows through the side overflow duct, goes straight into the rain head, and then you still never know about the problem. So the whole point of having the overflow discharging visibly to atmosphere is to alert the building owner or occupant that there is a blockage and it needs to be removed. So by comparison, the downbuster side outlet and rain head combination, the side outlet is actually quite shallow. It's typically around 60 millimeters for a 300 wide box gutter. There's a very short, deep section of box gutter that goes through the parapet wall, and this allows you to change directions into a rain head, but there's no penalty in depth, so you don't end up with an unwanted bulkhead beneath the sump for the pipe. The next topic is valley gutters. There's been very little research ever done on valley gutters. The code is very limited in what you can do. The maximum catchment area is limited to 20 metres squared. Roof slopes must be 12.5 degrees minimum. The nominal sidewall slope is taken to 16.5 degrees, and a freeboard of 15 millimetres is assumed. That's significantly less than the other freeboards, but then valley gutters tend to be fairly steep and much more self-cleaning. Now, when a situation that comes up relatively commonly now is that you have roofs of different slopes intersecting. For example, in this example, a 38 degree roof intersecting with a 14 degree roof. Now, the geometry to determine the sidewall slopes is actually, I thought it would be easy. It's actually quite complicated, and the answer is also not very intuitive. In this example, the lower sidewall slope is only 4.3 degrees, which to me was a little bit surprising. And it's a problem that the industry needs to address somehow. I'm not sure what the solution is going to be ultimately, but one answer may be to have you don't want this leg to be too long because they'll end up fixing the roof sheeting through it. One answer may be to have a slope of, in this example, say 4.3 degrees, and then a vertical section on one side, but that might require adjusting the roof patterns. But yes, it's just an interesting problem that is cropping up quite regularly now. The next topic is access to box gutters for maintenance and cleaning. Now, eaves gutters have continuous overflow provision, and if properly installed, such as having a 10 millimetre gap at the rear of the eaves gutter for a high fronted gutter, they can just overflow and the water runs down the facade and that's not a problem. Box gutters, on the other hand, when they overflow, the water goes straight into the building. Now, in this example, I've just called these concealed box gutters. I just seem to be seeing these more regularly at the moment. But I think I really think they're not a good idea, particularly for second stories. It's extremely difficult to access these for cleaning. And particularly if you're in a leafy area, you really need to clean out your box gutters. But that's very difficult to achieve for this arrangement. Now, an interesting question is, are architects responsible for ensuring safe access is available to clean out box gutters in the future? I've started exploring this question. I don't know the answer to it. A building surveyor found the article on the right for me, and you can just Google that and read that. I did call WorkSafe Victoria, and it appears to be a bit grey. I'm not sure what the answer is at the moment, but it's just something that just needs some consideration. I mean, does the architect need to document safe access, such as anchor points for rope access, where cleaning can really only be carried out by contractors with rope access qualifications? So the next item is just a couple of design examples. In this first example, we sort of had butterfly roofs with all the water draining right into the centre of the building. Now, the flow rate to that sump ended up being about 21 litres a second. If the roof drainage to this had not been designed and documented properly, I could just see this being a disaster on site and very difficult to fix. This was actually quite a recent project, and the solution ended up in this case we spread the. I'll just flick through the next slide quickly. We spread the water from one roof, the larger roof, onto the smaller roof, and that got the flow rate down below 16 litres a second. And we're able to introduce on the left-hand side, there were trusses, and it was possible to introduce a box gutter and a couple of rain heads to reduce the amount of water flowing to the centre. So I guess my point is that it just, you cannot do this once the trusses are up. It's got to be done at building permit stage. And I see this so often. And I've done a lot of roof drainage designs, and the hydraulic aspect is really the easy part. The difficult part is making sure that the solution is acceptable to the architect, coordinated with the architectural design and coordinated with the structural design. So was in this case, that's the additional the box gutter that was introduced, and that really just means that the roof truss framing needed to be altered a little bit. Just still on this example, I just wanted to point out one aspect of the dambuster sump is that it has a what's called a sump deflector cover, so that what that does is stop nuisance flows. So water that would ordinarily flow directly from the roof sheets into the overflow compartment, which is 200 millimetres wide, and cause nuisance flows in this sort of outdoor living area, is actually diverted with this cover and flows into the primary compartment. And so that can be quite useful at building entries, for example, where you don't want to see these nuisance flows. This second example was a little bit unusual. We had this is a second story roof with a curved canopy at the second story, trying to work out how that could be drained properly, and the solution ended up being a side outlet, dambuster side outlet, going into a dambuster sump. It's a slightly unusual combination, but it worked. But again, the point is that just, it's possible to find solutions to these unusual problems, provided you think about it at building permit stage. And the final example is a childcare centre. Now, in this example, we had was quite, and it actually doesn't get any more complicated than this, but we had a little parapet wall and box gutters either side, and there was, excuse me, the so that we had a downbuster sump on the inner side, and that the downpipe for that, primary downpipe for that, was directed into the main compartment of the rain head. The overflow downpipe was directed into the overflow compartment of the rain head, and a similar arrangement for the smaller box gutter. And that's a view in plan. It looks a little bit complicated, but it works. But again, it's just a matter of sitting down and thinking about this properly. So it's really amazing the extent of non-compliance in the industry. I don't know why. It's not terribly well understood. I think, the cost to the industry is enormous. It probably, it would rival the cladding debacle, but it's just not as well understood or known, and maybe that's because it doesn't cause, well, not directly injury to people. I mean, it could indirectly via mold, but it's not, not quite the same as the consequences of incorrect cladding. So here's an example of as mentioned before, this type of arrangement occurs all the time, where you have the plumber is meant to install a high capacity sump, but instead just installs a non-compliant standing overflow pipe, which is in this case it's a pop, so it's only an inverted pop, so it's probably only about 40 millimeters high. That entire sump, because it's near the bottom of the sump, that entire sump could get blocked with debris. And then the silly thing about this installation too is that the overflow pipe goes straight into the rain head, and again, if you get a blockage in the primary downpipe and the overflow pipe operates, you don't know that there's a problem. But this is on a very expensive house in Toorak. It doesn't matter what size the building or how expensive it is, the problem is just extensive and endemic throughout the industry, and it's really time that the industry did something about this. So the last item is from where I see it, what needs to be done to fix the roof drainage industry. So the first point is building surveyors and certifiers should require detailed roof drainage designs where there are box gutters to be submitted during the approval process. I note that the VBA has recently issued recommendations for Class 2 buildings, which include the required level of documentation for roof drainage, and I think that should be extended to all classes of buildings. As I mentioned before, roof plumbers should not be responsible for roof drainage design. They should be installers only. In my opinion, the roof drainage is a state addition to the PCA in Victoria and Tasmania only. In my opinion, it just should be removed. They just shouldn't be doing it. If for no other reason that it's too late in the process when they get involved. AS 3500.3, it needs, I believe, some improvements. It should clarify that the box gutter depth applies at the upstream end. So commonly I'll see the hydraulic drawings that specify they might specify for example, a 150 deep by 300 wide box gutter, and that's it. They don't specify the upstream and downstream depths, which are critical. And that if you only have 150 if you only have one depth specified, it's not clear to anyone as to where that applies. Is it at the downstream end? Is it at the upstream end? How is the fall taken into account? There's a misinterpreted clause in HB 39 that says that the box gutter depths can be 75 millimetres at the upstream end, which is actually incorrect. That only applies in one very specific case, which is a 600 millimetre wide box gutter, 3 litres a second, and a slope of 1 in 40. But that's the only case it applies. The code should clarify how box gutters are sealed to rain heads, and it should clarify the freeboard. Now, I'm only aware of the freeboards implied by the code because I've had access to the research papers in the 1990s. The code is quite misleading on this. It's not technically incorrect. It just says that the freeboard should be 30 millimetres in accordance with figure H5, which was the sump and side outlet. But that's that 30 millimetres is correct, but only in one very specific case, which is the overflow condition for the sump and side outlet. So it can be easily misinterpreted as being the freeboard is 30 for all devices in all conditions, but it's not. So I don't know why that hasn't been clarified in the code. So the next point is I think there's a significant amount of education is required regarding roof drainage in general. I'll give you one example is that I think sometimes architects tend to think, oh, a wider box gutter is better, but that's if you specify a 600 wide box gutter on your drawings, the box gutter cannot be reduced in width at its outlet, so that becomes problematic. And really, you know, in most cases, a 300 or 400 wide box gutter is more than adequate. But it's yeah, I think education is required across architects and building designers, civil and hydraulic engineers, building surveyors, and builders. The minimum information to be provided on the design drawings, which I think should be provided, are your assumptions in terms of the design rainfall and intensity. Very importantly, upstream and downstream box gutter depths for all box gutters, details of all box gutter overflow devices, details of box gutter changes of direction devices, and yeah, for ease gutters, minimum requirements. But I suppose just to end on the important point is that the coordination of the roof drainage design with the architecture and the structure is essential and needs to be done at building permit stage, and it needs to be done properly, and you need to ensure that you fully understand the solution and that it fits within the architecture and the structure. So I think really there's no longer any excuses for why roof drainage should not be properly designed and documented at building permit stage. I think the days of roof plumbers trying to find a solution at framing stage are over. I'd sort of call that it's a bit of a free-for-all, and I just don't think that's acceptable anymore. Perhaps some better regulation by the regulator. One example that really stands out is performance solutions for roof drainage need to be properly prepared. And currently, my understanding is that they are not reviewed. If a roof plumber ticks performance solution on his compliance certificate, there's no checking process for that performance solution. The VBA tells them they need to just keep the documentation for a number of years, but I believe that any performance solution should be listed on the certificate of occupancy or the certificate of final inspection and be available to current and future owners through the council if necessary. So that's the end of the presentation. Just wondering if there are any questions.
Thank you, Rowan. I will allow some extra time for questions if you can put those in the Q&A if you wish. Can I suggest we go back also to the first slide where we have the QR code? So for those who have joined later, we can allow you to log in. Also, you will see on the chat that we have shared the link, so you're able to complete the questionnaire, but primarily to register your presence here. Whilst I wait for any questions, I thought this was very interesting, but it also has highlighted the complexity of designing something that, in practice, you might consider a very simple matter, right? A design of a flat roof, although not roof is really flat. So my question would be, first thing, Rowan, would be, it seems to me that we must have, as architects, we need to consider very carefully the role of hydraulic engineers, perhaps, to be involved in projects, no matter how big projects may be.
Oh, look, I think so. I think, you know, I think, well, firstly, I think the hydraulic engineers perhaps need to, you know, improve the quality of their documentation for roof drainage. I don't think it's that well done at the moment. As I say, one glaring example is not having upstream and downstream box gutter depths on the drawings. I think they've got to get used to providing performance solutions for you know, outside the code, because the code is so limited. And I, you know, I think the well, it's traditionally the architect's role to carry out coordination, and they need to ensure that they have all the information from their hydraulic engineer or whoever's doing the roof drainage design, that they fully understand what that design is and ensure that it meets their requirements. It fits within their, you know, aesthetic requirements and fits within the structure. And you just cannot leave it up to the roof plumber.
Absolutely, that's a very good point. And you mentioned also the idea that it's important to document the roof system, because very often, you know, there might be a misperception that the details of ordinary functional requirements within the roof might not be necessary. There's been probably a tendency in the past to assume that things will be simple enough for anybody to resolve. But as you point out, there are elements of lack of coordination beforehand that make some solutions to become impossible, right?
I think, you know, architects very commonly show well, I'll call it an indicative box gutter layout, and they might show an indicative sump and an indicative rainhead, and hope that somehow magically that it's all going to work out when the plumber works out how to install a compliant solution. But it's just simply not the case. There's just so much non-compliant. It's staggering the amount of non-compliant work that is out there at the moment. And as I say, it unnecessarily costs the industry so much money. And you know, it's not just the cost; there's an emotional cost too. If a young person buys a new apartment, and that starts leaking, they've spent a whole lot of money buying their apartment. They've suddenly got to, you know, join forces with other apartment owners, engage experts to determine what the problem is, engage lawyers. It's a long, drawn-out process, and it just shouldn't be happening in Australia, but it is.
Yeah, no, it's absolutely unacceptable. In fact, the first picture you showed, they were quite compelling. That it's surprising to hear that this should happen.
Yes,
where we are,
yes.
given all the.
I don't know why. I'm not quite unsure why it's not that well understood. I mean, if I mentioned the Shergold and Weir report, the water ingress into buildings via roof drainage, it just seems to be lumped in together with, you know, balconies and bathrooms, which are, you know, completely separate topics, but it wasn't, just was not well separated, and it just needs some more research to actually understand what the problems are at the moment.
It's a very good point, because a lot of debate about quality of building has been skewed towards the Class 2 apartments, which of course have typically one big roof at the top.
Yes.
Whereas, as your presentation points out, it's a more widespread problem also in all sorts of building typologies.
Very widespread problem. It's very, very common.
I mean, we could continue to talk a lot more about this. So, Rowan, I take the opportunity to thank you on behalf of the ARBV and all the architects here in Victoria for giving us this presentation.
Thank you for the opportunity to
we
talk
very
about
much, yes, we very much appreciate it. And yes, there was one question that came in the chat if the ARBV will continue to do CPD more frequently. Well, we intend to, yes, do more. So bear with us. We'll endeavor to provide more opportunities like this. So thank you, everybody, and I wish everybody to have a good afternoon. Thank you.
Thanks very much.
You're welcome. Bye.